All right, so today we will take up this topic that's on integer-based vulnerabilities and format string vulnerabilities. Now note that there are large number of vulnerabilities that are possible. However, we are looking at only few, and then because we need to go into other topics, we need to study other topics, we cannot go into great details of many of these things, but pointers, I will give pointers, and then you can go ahead and do some assignments by yourself. Okay, a lot of information is available, so you can actually try to do something of your own, and actually you can try to find the vulnerabilities in commercial projects also. Okay, kind of and then you can participate in those programs wherein the companies big companies give you money for finding bugs. Okay, all right, so we'll look at these two vulnerabilities, and after this we'll move on to next topic. All right, so I have taken contents from many places. Of course, primary text for this is this lecture from Berkeley, from course 161, and this one very interesting book which I have purchased, and then also subscribe to the courses on it's a commercial video courses are available in on net. Okay, and then I am also doing those courses for my interest. So now this is by Professor Wen Liang Du from University of Syracuse, and he has written this interesting book wherein he has taken only hands-on approach. Okay, and most of the exercises are based on Linux. Okay, so you can go to this website and then read it from there. And of course, this is another book you can find on security, which is also very interesting book. So you can actually download this. This is freely available. Wherein Professor Du's book is not freely available. Okay, but the PPTs are available on the website. So and the book is I will try to procure this book for our library, but in rest of the course we will be using this book very heavily because it gives more hands-on approach, so I can cover the topic and give you pointers to read from the book and do some experiments. Okay, and note that in this course we don't have lab, so you'll have to work by yourself. If you really want to do hands-on approach, hands-on activity and learn about security, but there will be few assignments, and I have been given only one TA, and Pavitra is the TA, and so I can't overload her with too much of work, so there will be limited number of assignments, and rest of the problems that I will give, you'll have to do it by yourself because it will help you in learning. Okay, all right. Okay, so we'll cover these three topics, that too in very brief. We'll not go into great details. Okay, and try to finish the lecture early today. Okay, so first is integer memory safety vulnerabilities. So you have used integer, right, in C? Do you see any issue out there? What kind of problems you can think of when using integer? Anyone? See, when you have to do programming, see, most of you will do programming sooner or later, right? In your industry work. I would think most of you, unless you are planning to go for non-programming jobs, like becoming system admin or maybe configuration manager or maybe HR manager or do MBA or something like that. But all of us, most of us will have to do programming. And it's very good idea to do safe programming, right? So given a job, you will have to think whether to, what kind of, whether you'll have to use real numbers or what do you call that, floating point numbers or integer number or signed integer number, unsigned integer number, long or just simple int. Then if you are using int, you'll have to think is int machine dependent, is 32 or 16 bits or 62 bits. Okay, all these decisions you'll have to take. Say for example, if you are doing coding for something, some problem where there can't be negative number. Numbers are always starting from 0 to whatever number, right? Then why do you want to take in that signed integers? Because that will increase probability of error, right? So if somebody wants to cause a crash of your system or something like that, will give as an input negative number. Okay, and then it can cause problems. Okay, so say for example, you are copying array from one point to another point and then the value is negative. Then there is, so, and it being C language, then it will do something, and that something is what intruder or or malicious code may want to do. All right, so let's see. So all I'm trying to say is that when you write a program, just think in terms of whether it's safe. Okay, so let's look at it now. And very good number of bugs come because of the integer vulnerabilities. And yesterday we have seen the list. You will find some, at least one of the most common bug is overflow or underflow bugs. Okay, so is exploitable code sequence due to integer bugs. It means that if you are doing some arithmetic expressions or some calculations and there is a bug out there, then it also can cause somebody, okay, to exploit that. And so even is a integer error or integer conversion or integer bug, code can be injected or machine can be crashed and so on, right? All right, so they arise due to arithmetic operations. Side effect of type conversions. Okay, what is a type conversion here? So integer itself is of various types, right? We have seen the short, int or long, but I don't know, in different languages, high level languages could be very different. Essentially 16-bit, 32-bit and 64-bit length, right? Okay, or it could also be signed type or unsigned type. Okay, so and then we are using these number interchangeably. So there is automatic type conversion that happens in C, is done by compiler. Okay, and that conversion may be not appropriate. Okay, so if the conversion is between signed and unsigned, then there can be problem. What do you use for signed numbers in general? What type of representation? We studied in architecture course 2's complement, right?
Yes,
Okay.
yes, sir.
Okay, and then the unsigned one we don't use 2's complement. And with this conversion, right, or casting, then there can be a problem, right? Because see, ultimately in memory is just zeros and ones. Please note that, right? Everything is 0 and 1 in computer, right? In memory. While we may represent it by these zeros and 1, and they can actually semantically mean something different. That difference exists because the way it is interpreted. Okay, same zeros and ones can represent integer or floating point numbers, and it could be short integer or long integer or so-called double integer, double size, and all that. Or it can represent character. It's left to interpretation. Okay. Now, if the interpretation of same thing is with respect to 2's complement, while the zeros one actually represent unsigned number, then there can be problem. Okay, and these problems are left out by designer of C and C's compiler because it gives power, and many programmers use this so-called, which we'll call weakness, as a power, do things efficiently and quickly. Okay, so note that integer based vulnerabilities don't involve any injection of executable code, shell commands or scripts, right? So in general, you can just read some value or overwrite over some values. However, there are some methods available, along with some other vulnerabilities or methods. We can also do code injection, but largely it is used to get some data out of memory or corrupt the system. So they are different from buffer overflow vulnerabilities. Okay, so we will focus largely on C, although these problems exist to some extent in other languages as well. Okay, so now the free conversion and operations between different integer data types is actually dangerous thing. Okay, because C is weakly typed language. So in your compiler course, or maybe theory of programming languages, if you study it, then you would come across this word called loosely typed language and strict type, strongly typed or strictly typed language. Okay, so C is loosely typed language. All right. Now, interestingly, C allows operation between different data types. So can you add, say for example, a character, you define a character, which is 8 bits, and add this to an integer, a signed integer. Can you do this? Anyone?
Character is stored as an integer value.
Yeah, character is stored as integer value, so you can do that. But it's a compiler will not mind you doing that. But if you don't do it correctly, then you are in trouble. Then you are leaving some holes or gaps. Okay. All right. Now, why we are focusing on C? Because C is used everywhere. Although you may say you are using Python, but tools for Pythons are generally written in C. Okay. So interpreters for many of these languages are written in C. So C will come into effect sometime or other. Okay, and there's a huge installed base of the software. Almost all operating systems are written in C. All system tools like compiler, interpreters, etc., all are in C. Large number of applications are written in C. Most of the networking software, I would think, almost 90% plus, or even more than that. For routers, switches, etc., all written in C or C++. Both are similar in terms of security. Okay, so if you can find holes, then you'll have to, if you want to find holes, then you'll have to target usually something that's written in C, because it's much easier to find holes. Now holes are not because of the programming language is bad, it's because the way people have written the code. Okay, all right. So what happens is that somebody writes a code. The normal process of software development in industry is that, given a task, what do you call that, some higher level story is given. Okay, or it's called requirement, software requirement. Okay, from that design is done, from design, detailed design is done, then coding is done. Okay, and coding is usually done by one person. Okay, and then code review happens. Okay, and then code review in many companies happen just for namesake, and then there is a testing phase. Unit testing is done by programmer, then system integration testing is done by different team which are testers, and which looks at the system aspect, little detailed aspect, and then regression testing is done at the requirement level. Okay, so these are, and so it's very easy for, no, if the reviewers are not good and so on, it's not done properly, or even if it's done properly, there's a good probability that these wrong programming or the holes that can be invisible for very long time. And once software starts working, then then nobody really looks at it, what's exactly happening. Okay, so this hole remain in the system for very long time. Okay, you will find that some holes that are being discovered were introduced some 20 years back. Okay, so most of the software now, the problem that we have is that size of the software is increasing every day, right? Even mobile phone is 10 million lines of code. Even a small a car will have say 30 million, 20 million plus lines of code. Even a toaster will have 20,000 lines of code. Okay, something like that. Okay, so even home router will have the one that interfaces with service provider will have close to 5 million or 10 million lines of code. Okay, so now there is a continuous churn happening, and because of that many of these bugs remain, which you as a security expert has to find it out. And criminals also do parallelly try to find out these bugs. Okay, and there are tools available to find these bugs. All right, so coming back, okay, let's look at the char data type, right? It's 8-bit, can hold one character, and it can be viewed as integer type. Is commonly many programmers use in simple arithmetic expression. Okay, so basically when we are using different data types within an expression, they are converted into one type. Okay, and it's not done at runtime, it's done at the compile time. Okay, if the language is compiled language like C. So we can see char here in this table, we can see different data types which are basically integer type. So we can see char is of 8-bit length, and the range is, again, char can be signed or unsigned. Okay, it can be 0 to 255 or minus 128 to 127. And then you can see range for short integer, long and so on, long and so on. Okay. Now if you use an integer, okay, and then there is some maximum value, okay, and then you try to further use a number or try to store a number which is bigger than the maximum value, then there is a problem. Okay, and C will not find this out at compile time. Okay, so now for example, for the char data type, there are different types, 3 types: signed char, unsigned char, and char. Okay, signed char, unsigned char we have seen here. Of course we are not shown here. Okay, and then char is Now, one loophole is that chars, if you use simple char type, these are machine dependent. Now, if programmer is not careful, then there can be errors here. Okay. So this type conversion, when it's it can be done by compiler if it's not done by programmer, or it can be done by programmer. Okay. For example, unsigned integer is 0 extended. We have studied that, right, in computer architecture course. And when there's a conversion from a smaller conversion to smaller width, then there's a truncation. Okay, so first thing is basically sign extend with 0. Okay, and if conversion between signed and unsigned integer changes the interpreted value. Now this is most dangerous thing between signed and unsigned. Okay, so look at some few things, right? Look at this code. Is there a problem here? So this mem copy have you used? Mem copy simply copies a number of bits, number of bytes from one memory location to another memory location. So basically, you can say string copy equivalent. Do you see any problem in this one?
Length can be negative.
Length can be negative. That may not cause much of problem. Okay, good. What else? Okay, that can cause some problem. Yes. Okay. It is not safe, surely, because I'm showing it here. Otherwise, we'll not discuss. Look at so now we're not bothered about what mem copies format of mem copy is. Okay, we are assuming the length here. In when we define mem copy, basically is a function. Argument for mem copy here, it is what? It is signed, because integer here is signed integer, right? So it can be plus minus. Where here, when you define mem copy, here the argument is unsigned. This comes here, just a minute. Okay. Here it is unsigned. Size underscore t is basically unsigned type. Okay. So what are we doing? We are converting signed one. We are giving signed values which correspond to signed into unsigned one. All right. So this value will be interpreted differently here. Okay. So what happens if length is -1? Okay. So how you will represent -1 in 2's complement? Anyone?
1 1.
No. -1 in 2's complement will be FFF, right? Okay. So this value will be passed here. So -1 becomes FFFF, whatever. Maximum value that can have, right? Okay, there's a maximum that you can represent in whatever, if the machine is 32-bit. Okay, so what's happening now? This length of the data you can write over buffer. Buffer is of 64 bytes. And this could be very large. Okay, and where is the data coming from? Somebody in the function, some main program, you are giving this data. Okay, or it may be being read to stdin, or or standard input, or keyboard you are typing in. And if you type it very long, of course, which can be as long as you know this maximum length defined by FFFF, then you can overwrite, right? So it's an overflow problem, buffer overflow problem. Okay. So now you can cause buffer flow by simply you know if programmers are not careful about using same type of data type here. All right. So one place it is function. Of course, mem copy you cannot change. You cannot change this, right? It's given in library. So now and it uses this kind of data type. So you have to be careful about using appropriate data type and when you are defining a function. So change it to size tn and the problem will go away, like here. Okay. All right. Any question? Note that these are just examples illustrating the concepts. Just the concept, right? Don't get into great details of understanding semantics of what else it does, right? So right now we are focusing only on what kind of problem can be caused, although seemingly program looks correct. Okay, and then cyber criminals know all about this, right? They try and there are tools available to exploit this kind of weaknesses. All right, look at this one, this code. Do you see any problem here? So this is okay, because you know when you do malloc and it returns 0, it means that something has failed. It does not have enough memory. So you will get 0. So minus 0, sorry. So here it becomes 1. Okay, so if malloc is not done, then it will return. So it's okay, assuming that this condition is not executed, the malloc is done. And then it's available at buffer, a buffer string, right? Or pointer to that buffer. Where do you see a problem here? If you are a code reviewer, you are reviewing the code written by your team members, then where you will find bug in this one? Anyone, please attempt. Huh? Advait, can you try?
Sir, I think in array we can give side number as well, like buffer of length.
Mm-hmm.
In
No,
that,
here focus is on, you look at what, we're not focusing on conversion as we have done last time, right? We are now looking at the limits. Okay. I mean, given 16-bit character, or say 16-bit or size t, whatever, let's assume it's 16-bit. Okay. Then are we trying to do something which is beyond 2 raised power 16 minus 1? Beyond this, are you trying to do this? That we'll have to see. So when you do the code review, just see what kind of integer is defined, and you see the is any operation has a chance of taking up a value which is larger than that. Okay, now let's see. Okay, it is not safe, because if len, something that we're defining it here, happens to be the kind of maximum value. Note that it is unsigned, right? This unsigned integer. This is also unsigned. So now if you add 2 to this one, what will it become? Okay, it's kind of 1, right? 0 and then 1. It means that now you are allocating a buffer of size 1. Okay. and now you are writing to this buffer through mem copy data. Okay, now data can overwrite over the buffer. So again we have a buffer overflow problem, right? Oh, so here in case of heap overflow, because it's actually in the heap. Malloc we do in heap, so well, yeah, is kind of not stack overflow but buffer overflow in the heap. All right. Okay, got it? Any issue in understanding? Look at the code again. Now, if you give this data, because this is in your hand, right? Because you are calling this function somewhere, or malware or some process or somebody can give this data, then it will give some data string which it want to insert in buffer. Okay, and this it could be anything. All right.
Sir,
Yeah.
will it show like segmentation fault error here?
Why?
Because you are using memory which is out of its like range.
Where is it out of range?
Like
Yeah. So
buffer.
now the problem is that how do you implement heap? Or does it check? Does it do any runtime check? Because now it's all happening. Data input is happening at the runtime, right?
Yes.
So there is no segmentation fault here because heap will allocate. This process 1 byte is allocated, and you are trying to write more than 1 byte. There must be see, there is a space available in that heap region, right? If you look at this, the runtime image, then we have whatever code, then static, and then heap. This area is allocated, right? It's available. So this exactly like a buffer overflow problem, because you are not doing bound checks here, right? System does not do bound check, and hence there is a problem.
Yes, sir.
All right. So there's no question of segmentation fault here. Okay. All right. So there will be heap overflow, and there have been a lot of problems in actual practice when people have written application, and one application that people have written for vote counting, and they have used inappropriate or smaller values of integer, say 16 signed integer of size 16. Okay, and then number of votes that were casted were more than that, so effective result was a wrong result, right? And this happened somewhere in US. Okay. All right. So maximum value, then if the signed integer of size 16, machine integer is of size 16 and signed, then approximately half numbers will be on each side, positive and negative, and number of votes are more than this, then there is a trouble. Okay. All right. Let's go ahead. Okay. All right. So please go through this chart where it shows different kind of vulnerabilities like integer overflow, integer underflow, signed mismatch, signedness mismatch, narrow loss, expansion value change. Or so please go through this. So it's taken from a book. Okay. Now let's go to second part of discussion, right? It's called format string vulnerabilities. Now these are again vulnerabilities that have been exploited a lot. Now when we say format string, it's essentially we are talking about printf. Okay. So if you notice, printf is a function first thing, right? Okay, when you do printf, actually it goes to a function, control goes to a function, and that executes, and arguments for that printf is that you specify. Okay, here you specify format control string, and arguments, other arguments. Okay, and format control string describes the way the output will look, and from that actually conversion can also happen, right? All right, all right. So here we specify in that format string conversion specification, right? We specify what, say when we say what do you call that, percentage sign D, whatever we corresponding to this, there is some variable we defined here, arguments, whatever it is, say some count or something, it converts into this type. Okay, integer type, signed integer type. Okay, so and if you define this as something else, then it converts into that type, right? So basically that's the reason it's called conversion specifier or conversion specification. Okay, and then we define other arguments, and these are the conversion specifiers, D, I, O, X, H, and so on. You might not have used many of these, and there is something also which is not defined here, is called N. Have you used ever this conversion specifier as N? Did you use it? If not use it, please try to do that. Okay, let's look at this printf behavior. Okay, so it's like this. This is a function. Okay, and you define integer secret is an integer, and assign value of 42, and then execute this printf percentage sign D / n and 123. Do you see any problem here? Okay, before that it will go something like this in a stack. Now note that it's a variable, right? Okay, so it will go something like this, that when it comes here, then 42 will be stored here, and then argument of this will go, because we know that when there is a function call, then the argument of those function call will go first. So 123 will come here, and this is also a argument, okay, which is a specifier, will come here. Okay, now note that this is something that is not going to change, it's an invariable part. Okay, if the string changes, then the whole string will be here, otherwise there will be a pointer to that, and this will go into the static area. Okay, you recall again runtime image or process image. So there is a static area where the static variables go. Something that does not change, a string that does not change, is kept in static area. Okay, so now okay, so coming back again, do you see any problem in this statement? No, there's no problem. Okay, it just it tells where things are stored. So now what we'll do is that when it's going to look at this, when the program is in execution, this function is execution, looks at this specifier D, it will look at the argument here, and this argument is stored here, the value, this is argument 1, so its position is known, and it will, as a result of that, it will print this, whatever is here, print it into terminal. Okay, all right, no problem. So you know, so the moment you it while scanning, it will find this, it will print this out. If there are two specifiers, then it will look at also something that's above this and print that out. Now with this understanding, let's see where the problem can happen. So printf assumes that there is a one argument, okay, because there is a one format sequence, and we'll look at 4 bytes up in the stack for the argument, the one which we discussed just now, right? It will look at 4 bytes up and then print this argument 1 out. Okay, all right. So what happens if there is no argument? It means that now you give this one. Okay, so stack is as follows. Okay, and there is no argument, so there is nothing as argument 0. So argument 0 is this one. There is nothing above this, right? Okay. Okay, so ideally there should be one argument here, as we have seen earlier in this case, but there is nothing. So what will happen now? You understand where the problem is? If you don't specify an argument here, there's not a problem in C design, right? What we'll do is that look at something just 4 bytes above this one. So 4 bytes above this one is this. Yeah, secret is equal to 42. Yeah, somebody is please mute your phone. Okay, all right. So it will print 42. Now, which is the secret number? Here, as per your definition. Okay, all right. Now the question is, why will you do this? Okay, all right, but there can be scenarios where this is possibility, right? Now the one scenario is like this: something that is going to be as arguments, specifier and arguments of printf function can go as a string. Okay, and that string you can give through input, right? Okay, so it's like this. So you define buff a string of 64 characters, and then here in this function, vulnerable function, you get fgets from your keyboard 64 bytes and store this in buffer, and you're putting this buffer as an argument of printf. Now whatever you want here you can give, and then it will go here in printf function, right? So this buff in printf. So this you are giving, this it means a specifier and arguments you are defining. And here you may want to omit this, or you can play with this, right? Whatever information you want from stack. All right. Okay. Okay. Let's go ahead. Now let's assume that this string you define that, here you are able to, input this string, which is basically specifier and also what do you call that, arguments. Okay, so this one, if you intelligently do, then you can cause some problems. Okay, sorry. Okay, all right. So let's see that what kind of problems you can cause. Suppose you give this string as the one here. Now what will happen? Now this will be taken as input or a specifier. Okay, and then it will look at 4 bytes up and print that out. Okay, all right. Okay, so now let's assume that if you give input as 100 %sign s, this one, then what will happen? So it will print 100 and then look for this one in argument. It will not find it. Then it will go up. Now it's a string. So we'll get in a stack a pointer to the string, or string or pointer to the string. And if string is, for example, in heap, then it will print that out. Okay. And if you give this kind of input, percentage X, percentage X, percentage X, and so on, then it will do some other kind of printing. All right. Okay. So now you can go to this example, which tells what kind of problem you can get exactly based on what we have discussed so far, right? So for example, there's a buffer of 64 byte size, and there's a vulnerable program, and then a string which you define as pancake, and this is secret string. It's evident from this one, right? And then secret number, you also define secret number as 42, and then you do fgets buff 64 std in. Now here, if you give appropriate input, then you can come to know what is secret number and what is secret string. Okay, all right. So that's all it says, right? So for example, if you give percentage sign D and percentage sign S, then you can get for corresponding to D you will get 42, and corresponding to this one you will get pancake. So you can get both secret number and secret string. All right. So please go through this example by yourself. Okay, all right. And then we have a lot of vulnerabilities with respect to percentage n, which gives you some number back. It does not do, it's not really a format specifier in, but it gives you, some number. So basically, it gives the number of characters before this sign appears in the string. Okay, all right. All right, so you look at this. So we don't have time to go through this one, but the example you go through this is all. Whatever I say, go through it. Actually, you will have to actually go through it because questions can be asked in the exam. And then there are defenses, right? So defenses essentially do proper programming. Okay, don't use certain things, right? Never use untrusted input in the first argument in printf and so on. Okay, please go through it and also read from the book. So advantage is that when you do programming in future, you will be careful about it. Okay. So what can you achieve through this? You can crash a program. You can print out data on a stack that we have done just now, secret number and secret string. Change the program's data in memory. Change the program data in a specific value and inject malicious code. Through format string vulnerabilities, you can also inject malicious code. Now, so please read it from the book, Wen Liang Du's book. So it's taken from that book, and they have given steps to achieve each one of these attacks. Okay. Now, how to inject malicious code? Again, a lot of information is available in the book. It can be done multiple ways through input string that's being read from keyboard. Okay, through stdin or something like that. You can do it through memcopy. You can also get that data from a file. If you open a file and you are reading it from file, and somehow malicious code is available in file, or you make it available in the file if you want to hack a system, then that can get copied into. So you can manipulate code injection in simply by copying data from file, and there are many other ways which I have not mentioned this. So please think about it. Okay. Now the question yesterday somebody was asking was how to jump to a malicious code. Okay, so there are a lot of hints available. It's not that there is exact science, right? You'll have to do a lot of experiments. So first thing is that you are within address space. Somebody, I think, I don't know who was, but that what happens every time program executes, it's in different area, right? So you remember one thing, that address space remains the same. Okay, and multiple processes have different, basically numbers are the same, but they are placed differently at different places in main memory. Now, when you say program counter or jump PC value or program counter value or jump to a location, and within the address space, okay, this is not really the actual physical memory we are jumping into, right? We are actually jumping in terms of this address is virtual address space. So, okay, so program counter always works in virtual address space, right? And the conversions happens later. Remember that diagram we studied in computer architecture course, right? So all these things, the addresses that we are using, a jump address, etc., are in terms of virtual address space. Okay, and then of course these are mapped through memory management to actual memory location, because each time your program counter goes up, okay, then it's that program counter value is given to memory manager, and then finally actual address is found out. That's the way, right? It happens. So the first question that you ask is that every run it will be different. No, it's not. It will virtual address of where you have to jump to will remain the same because you are within address space. Okay. Second thing is that, okay, okay, we are here. Anyway, just second thing that we are using relative addressing that I mentioned yesterday, right? So most of the programming that we do in x86 is relative addressing, is PC relative. So jump address is always with respect to PC. Okay, another hint is that stack usually start at the same address. You know, we say that the format of this, you know, runtime image is kind of fixed. So you can always find it out, right, with experiments. Another hint is that stacks are usually not very deep. So you can have, essentially it means that your choices where to jump to are limited, right? Okay. All right. And then this is generally few thousands of bytes in a stack. So the conclusion is that therefore the range of addresses we need to guess is usually quite small. Okay. Now suppose you are finding out an approximate address where to jump to, then one technique is that pad this up before or you know, but before that code starts, not really padding, but previous to that code, put all NOPs, no operations. When we run no op, we know that, right? When we run no op, then pipeline just moves, or we go to the next instruction. Nothing happens, right? So now if you, and this is your malicious code. So if your overall code is this one, and you jump here somewhere, and then you start execution from there, ultimately you'll hit on the malicious code, right? It's called NOP sleds. Okay, all right. So this is a concept. So if you approximately find out from all this information that's available to you and guess and so on, approximate address, and then when you inject a code, it will have sequence of knobs, then you are done. All right. So summarize, we have studied buffer overflow problem. We have also studied format string vulnerabilities, and it's because of printf. Now next, sometime or other, if you have time, then we'll see that how to define memory safety vulnerabilities. Like there are some methods like address space randomizer, which randomizes the address space, and there's something called canary, if I remember right, and there may be some more. Okay, so we'll study some of these maybe towards the end of the course, because by the time we'll look at some more vulnerabilities and we'll see defenses for many of these. Okay, any question? No? All right. Please go through the presentation and the book, especially Wen Liang's Deuce book. All right, it's a nice book.